Hello everyone, this is Mr. Teo again for EG3959. Today we are going to talk about the Lab7 submission. Okay, without further ado, let me start by sharing the screen for the presentation, PowerPoint presentation. Now, as you already know, Lab7 submission is on week 13. So right now is week 13. So we will start with Lab submission on PID controller design and tuning. Okay. Now, if you go to the Lab7 folder, you will realize that there is quite a number of things there, and it's quite a handful. Let me start by going through each of these. Of course, the first one on the list is the book plot student edition.vi. Yeah? So this is the VI that you can download to run your simulation. This time around, you don't have to do any connection. You just need to use the VI wholesale and then enter your transfer function and run. Right, so you'll basically be downloading this and use it to just run for the simulation result. Now, of course, for every lab, there's a lab sheet. So the Lab7 lab sheet is appended here. And the slides which is what I'm showing you now, is also appended to you. And also we have a step-by-step guide on how to do Lab7, which is given here. With all the equations and mathematics. Now, of course, this Lab7 submission is on 16th of July 2021, 6 p.m. But this is, take note, this is week 13. And week 13, it is not confirmed yet whether we have face-to-face or we will have it at, or we will have work from home. So, of course, if it is work from home, then I will delay the submission by 1 week. That means the submission will be the subsequent Friday. That means it's not this Friday, another Friday. So that everyone will be able to come to the lab to do the submission. But prior to that, there's a lot of theory and calculation which you can take a look at it first, because this particular Lab7 theory and calculation is pretty complicated as compared to Lab5. Now, to begin with, as recall from last lab, which is Lab6, we have did the motor module, right? And we and this time round for Lab7, we are just incorporating the controller portion, right? Remember in Lab5 submission, I told you to put the controller as 1/1 because we have not touched on the controller yet. But right now, we have proceeded to the stage whereby we are going to design the controller. Of course, I'm not sure what is the progress of you guys in reading the lecture notes. Some might be ahead of time, which is good, and some might be still not up to chapter 5 yet. But if you have not yet, please read ahead for this lab assignment. Now, okay, so for any controller, or rather a PID controller, we are using a PID controller here, which is P for proportional, I for integral, and D for derivative. And the design spec is as per given here, right? As per given here. Okay, so in the lab sheet, they have a specs from the customer also that desire this 3 particular specification. Now, from these specs, we can derive that zero steady state error means that we need to use an integrator, because out of the P, I, and D controller, only the integrator, which is Ki over S, will give us a 0 steady state error. So from this, we already know that the I component is there. Remember, in PID controller, we can choose arbitrarily which one we like to be in, so long as it meets the specs, right? So of course, right now is telling you that the I part of the PID controller has to be in order to have 0 steady state error. So this is a very big hint, right? Now, subsequently, two other specs. One of them is the maximum overshoot, or the maximum peak overshoot might be less than 40. So we know that the maximum peak overshoot formula from the data sheet is given, rather the formula sheet is given by this equation here, and then it must be less than 0.4, which is 40%, right? And also, it also wanted this last specification by settling time for 2% criteria, not 5%, must be less than 2 seconds. Okay, formula for 2% criteria is 4 over zeta omega n. It must be less than 2. So we can basically set up these two equations. So through these three specifications given by the customer for you to design, it actually prompts you to different equations to be used in the later part of your PID design. Okay. Now, recalling from the last lab, which is lab 6, we have did the potentiometer modeling, which is if you start to run and then you check out the model, it is given by some kind of sawtooth wave, and we have already derived it as G of S equals to 6 over S, right? And also in the tachometer portion, which is also in the same motor module, but the other output, we have something like a first order transfer function, right? And the expression is given by 0.58 over 0.2s plus 1. Oh, so this is the practical session on lab 6, right? Now today we are going to use this motor module to be in place for the motor that we are controlling. So therefore we replace the motor module by either this or this, right? Either this or this, right? Depending on what you are going to submit, right? Now, of course, for your submission, I'm not so evil to give you the more complicated first order transfer function. I'm giving you this, the lower one, which is 6 over S, is much more easier to solve. So your submission is basically focusing on G of S equals to 6 over S. Now, of course, with that, this we already mentioned in the previous slide. So now the problem is to choose what kind of controller do we use. Do we use a I controller because we know that the I controller is in, or a PI is possible, or ID, or maybe the most complicated is PID. Of course, the lesser the component you pick, the whole design will be simpler, but yet we have to make sure that it can satisfy all the criteria. Now let's quickly take a look. So we know that steady state error require I controller, therefore Ki over S is needed, and therefore we either can choose I controller, PI controller, or PID controller. Right? Now using rule 7 of block diagram manipulation, because this is a negative feedback, negative unity feedback, and therefore you use G over 1 plus GH. Now your G is G controller times by your motor module transfer function. So if you use a potentiometer, which is 6 over S times by GCS, right? So this is your potentiometer if you substitute in the 6 over S. But if you are using the tachometer, then you will substitute the other transfer function, which is 0.58 over 0.2S plus 1, right? So this is a closed loop transfer function that is already sort of like calculated out for you. Now, if you use an I controller, basically your GC, which is the controller transfer function, will be replaced by Ki over S, nothing else, right? Because your Kp and Kd are not in. So basically, you just replace the GC for the potentiometer and the tachometer respectively, you get Ki over S, right? Now, if you choose a PI controller, then your expression for GC will be Kp plus Ki over S, because you got a P term and I term, right? Kp plus Ki over S. The rest is the same. Now, if you have a more complicated one, which is PID, then you have a full suite, meaning that Kp plus Ki over S plus Kds. So same goes for potentiometer and tachometer, which you substitute in the previous equation. So that's how you get the equation to stack up, right? Now, again, let's come back to the maximum overshoot. Maximum overshoot needs to be less than 40%. So this is equation. With this, you can try to find out what is zeta. Of course, you got to work out this. This is only one unknown in the whole equation. You should be able to solve it, right? Solve for zeta. Now, with this zeta solve, then using the second specification, whereby they say the settling time 4 over zeta omega n is less than 2 seconds, you plug in your zeta here, then you have only one unknown. You will be able to find omega n. Now, when you can find the omega n and zeta, you can reconstruct the characteristic equation as S squared plus 2S 2 zeta omega n S plus omega n squared. Remember, this characteristic equation is the denominator of the second order generic equation. So you can reconstruct this. Now, once you reconstruct this, you can compare it to your closed loop transfer function. Closed loop transfer function is what we have just calculated, right? For each of these, right? These are all the closed loop transfer function. So you can compare it with the characteristic equation denominator, and from there you will be able to find out what is your Kp and Ki, right? So the steps is basically for your submission, you only need to do from page 1 to page 8 of your lab sheet. Basically is to meet the 3 specification, and we will only be doing for motor module is equals to 6/S. Basically the steps I have just run through with you quickly already, that you have to calculate zeta and calculate omega n and reconstruct your second order generic equation, the denominator, which we call it the characteristic equation, and then compare the coefficient of S squared, S, and non-S term to find out Kp, Ki, or Kd, depending on did you use Kd or you use Ki or Kp. So this is the Vi. If you use the template that is given there, basically you can just download this. But remember, you need not modify the front panel. Unlike the Lab 5, you have to key in the transfer function in the front panel. Here, you don't have to touch the front panel, right? The entry of all the transfer function is by double-clicking each of these portion here. For example, I want to change this to 6/S, I double-click the plant. Then an entry form will come out. So you can double-click each of these. Likewise, for the controller, you need to change it this time around. It's not 1/1. So after you calculate your Kp and Ki or Kd, if you have, then you get to key into here. So after keying in, you can straight away run. There is no need to change any other thing. Right? Now, this is just to recap to you what we mean by process dynamic for under dam situation. Now, usually under dam situation is when there is a picking. I realized that in your Lab 5 submission, a lot of people say that when there's a picking, when there's an overshoot, it means it's over dam. Wrong. When there's overshoot, means it's under dam. Over means under. Okay, so overshoot means under dam, and therefore these are all the parameters that we can measure from a second order under dam system. Now, let's quickly take a look. Now, it defines here as the rise time. Now, rise time is usually for the rise time from 0 all the way up to the final value where it's settled down, right? So this is what we call the rise time. Of course, there's 2 types. One is from 10% to 90%, and one is from 0 to 100%. So in the formula sheet, you can find 2 definitions for rise time, one from 0 to 100, one from 10 to 90. So this is what we call the rise time, how fast it rises up to the final value, right? Now, there is this time called the T peak, means that from 0, how fast it rises up to hit the maximum peak. So this is the time taken for it to go up all the way to the maximum peak. This is called the peak time. Now, settling time will be the time taken for it to go up and then settle down. Let's say for 2% criteria, it must settle down within plus minus 0.02, which is plus minus 2%. Now, if it is for 5%, then the tolerance will be bigger, and therefore it will be faster, right, to get in. Maybe around here you should already get into 5. So therefore, you can see that the 2 expression for settling time, one of them is 4 over zeta omega n s omega n, and the other one is 3 over zeta omega n. So the shorter one will be for the 5%, and the longer one will be for the 2% criteria. Now, of course, there's also the delay time. Delay time is time taken for the signal at the output to reach 50% of the final value. And then, of course, this is the maximum peak or the peak overshoot, which we always concern, and it is a peak raised from the final value. That means final steady state value all the way up to the maximum. How much is it? So you can see that we are dealing with under dam, and we have a complex conjugate roots for the denominator, right? Now, this with the under dam system and with the omega and zeta found, which is what you have did in the earlier part, you can go to the formula sheet. And these formulas are all in the formula sheet. I'm just lifting up from formula sheet to paste it into here to let you all see that actually all these formulas are available. Just now I mentioned about 2% criteria is 4, but 5% criteria is 3. So this is actually shorter time to settle down. This is a longer time to settle down because it's 2% criteria. And then this is for 0 to 100% rise time. This is for 10 to 90% rise time. So they have the two different formula. So if you are trying to measure 0 to 100%, please use this formula. Now, if you are trying to use find 10 to 90%, then you can use this formula, right? So basically, after you run the simulation, you got to make sure your specs is in, right? So the specs for this exercise, they want 0 steady state error, meaning that there shouldn't be any offsets here. So the final value and the input must be exactly at the same point. So you can use the digital display, visible digital display to see this error if it is 0. So this is one of the criteria, right? So you got to check the final simulation whether it's 0 here. Then whether this peak overshoot is really 40% of this whole thing. So if it's less than 40 or 40, then you are all right. And then also the 2% settling criteria means that the time taken from here to when it's settled down within plus minus 2%, it is less than 2 seconds. You got to make sure all these three happen, and therefore your design is already done. So you can submit. Okay, that's all for my presentation. I hope everything is clear. Okay, let me also share with you the wait a minute. Wait a minute. Okay, let me stop sharing this. Of course, you can see that the formula sheet is the equation for the second order underdamped system is given around here, right? This is for the first order, and the second order is given here. So if you go and take a look at the formula sheet in the tutorial, you will be able to find all this. Now, what I want to show you is the guide for the submission. Now, let me start to share the guide first. Where is it now? Now, as I have mentioned, if you are able to see this, guy here, you realize that there is a step-by-step guide of what I have just shown you, but it is more equation are given because I don't know eventually which PI or what, but the mathematics is given here to let you have a taste of how to calculate. And you can also refer to the lecture notes for, if you cannot understand this, you can refer to the lecture notes, or even read ahead of time all the way up to week 15, and you should be able to find the answer to many things. Okay, without delaying much of your time, I will stop here, and I hope you all the best. Thank you and bye-bye.